For the past few decades, scientists have been fascinated by what happens to matter at low temperatures. There have been many developments in the field of cold atoms, but now the interest is shifting onto cold molecules, where we can actually gain understanding in more complex systems and have a look at the chemistry.
The thermal energy available to molecules at room temperature makes them spread over many energy levels, and we can only see the average behavior. However, if we cool the molecules down to ultra-low temperatures, we can lock them into specific quantum states and therefore reveal their truly quantum behavior.
So Edinburgh's quite cold, but the temperatures we're discussing here are significantly colder. Cold physics is interested at temperatures around 1 Kelvin, and ultracold physics looks at temperatures around 1 millikelvin. That's 1,000th of a degree. Compared to the temperature here, it's like comparing this temperature to 5 times that of the inside of the sun. That's a pretty big difference.
So what is a temperature anyway? It's the measure of kinetic energy of the molecules, which tells us about their speed distributions. At room temperatures, the molecules move at the speed of rifle bullets. Whew, that was close. Luckily, at low temperatures, molecules move more like an ant, which is a couple of centimeters a second. Unlike ants, cold molecules behave more like waves than particles. This is a consequence of wave-particle duality, which is important for quantum systems. Which type of the behavior is exhibited depends on a quantity called the Broglie wavelength. Because the molecules are very light, and when we slow them down, the Broglie wavelength becomes enormous. In fact, 10,000 times bigger than in room temperature.
In space, simple atoms and molecules like hydrogen and helium exist at very low densities. The fact that molecules are so far apart from each other means that collisions between them are extremely unlikely, and that makes reactions more elusive. Studying molecules at low temperatures allows us to recreate those conditions of low-density particles in the lab. This is very exciting for the field of astrochemistry, which investigates how chemical reactions occur in space.
Before we examine the behaviour of these molecules at low temperatures, we actually have to be able to build them. There are two main strategies to building these molecules: direct and indirect methods. The direct method involves assembling the molecule and then cooling it down. The indirect method cools down the atoms and then assembles them into the molecule. An example of a direct method of producing cold molecules is buffer gas cooling. This technique involves thermalization of the required species by colliding it with a cold buffer gas to produce slow cold molecules in a stellar beam. The collisions between the buffer gas and the studied molecules dissipate the translational energy of the molecules, which is also followed by rotational cooling due to the inelasticity of the collision. Let's have a look at this technique in more detail. Noble gas molecules flow through 4K heat exchangers and are reduced in temperature using a pulsed tube refrigerator before they flow into the cell. We use laser ablation or capillary filling to produce the gas of the colliding molecules. Laser ablation uses a high energy pulse which hits a precursor of the studied molecules, and the resulting plume of material is our molecular gas. The molecular gas molecules collide and thermalize with the noble buffer gas before they both exit the cell, and also before the molecules diffuse to the cell walls. The molecules that are produced from ablation tend to be around 10,000 Kelvin, and so efficient thermalization has to occur within a few microseconds in the cell. Stark deceleration is another direct technique that can be used to produce cold molecules. The Stark effect describes what happens to degenerate energy levels of molecules with a dipole moment in an electric field. Molecules that show increases in energy due to the field are known as low field seekers, as they experience forces away from high electric field regions. Molecules that decrease in energy with electric field are known as high field seekers. Stark decelerators work by passing molecules through regions of high electric fields, where they will lose kinetic energy if they are weak field seekers, or gain kinetic energy if they're strong field seekers. The molecules will also increase in Stark energy as they pass through the electric fields. We can pass molecules through a high pressure valve nozzle into a vacuum chamber to cool them down to low temperatures, but with high speeds of around 300 to 1000 meters per second. The cold molecules are then passed through the decelerator. The decelerator uses a varying series of electric field gradients to slow the molecules down. Our polar molecule moves from a low electric field to a high electric field region, and as a result, its internal energy increases at expense of its kinetic energy. So, the molecule slows down as it climbs up the potential energy gradient set up by the electric field. The electric field is quickly switched and the molecule loses its stark energy without gaining back its kinetic energy. The molecule finds itself at the bottom of another potential hill. This process is repeated over and over to produce an overall reduction in the speed of the molecule. The technique itself works for both weak and strong field seekers, but strong field seekers are more difficult to focus as they crash into the electrodes at high fields. A Zeeman decelerator can also be used to produce slow cold molecules, and it uses the same principle and setup as we've just described for the Stark decelerator, but it uses magnetic fields instead of electric fields.
Photoassociation is one of the most commonly used indirect methods for producing cold molecules. In this technique, colliding atoms are exposed to laser radiation, which promotes them into a common bound excited state. Such collision would not be able to directly produce bound ground state, as no mechanisms are available to dispose of excess energy as the molecule falls down the potential well, so an additional stabilization step is required. As the cold atoms collide, the energy of photoassociation photon is tuned just below the transition energy between the unbound atomic ground state and the molecular excited electronic state. This ensures that the photon can only be absorbed if this state is reached. This process only starts here, however. The weakly bound state of the molecule is metastable and may decay in two ways. One option is for the molecule to redissociate back into its constituent atoms, and the other involves spontaneous transition into a ground electronic but vibrationally highly excited state. Both outcomes are undesirable. In the second case, the molecules may be produced in an incoherent mixture of different vibrational states. If a collision with another molecule occurs, the vibrational energy can be very efficiently transferred into kinetic energy, heating up the gas. To avoid this, another laser field is applied to stimulate a controlled transition into the ground electronic and vibrational state. We've learned that direct methods are useful because they can be applied to a wide range of molecules, which means that they have very versatile applications. However, producing cold molecular gases in this way demands a lot of imagination on our part to come up with new techniques and improve existing ones. Direct methods also have limitations in terms of how low can you go in terms of temperature, depending on particular techniques.
Indirect methods, on the other hand, are able to access ultracold molecules with temperatures as low as 1 microkelvin, and the techniques we use are well understood in the field of atomic physics. Additionally, the translational temperature of associated atoms is maintained because the center of mass remains unchanged, save for the little momentum imparted by the incident single photon. However, indirect methods require that special attention be paid to stabilization. Otherwise, we can end up with an incoherent mixture of molecules in different states, or heat up the molecular gas. As both types of methods have clear advantages and disadvantages, which one we choose will depend on which particular experiment we're interested in. So let's take a look at some experiments and what we can do with cold molecules. Many applications envisioned by scientists require that the cold molecules are stable in their prepared states and their lifetimes are long. For atoms with unpaired spins, this scheme is spoiled primarily by three-body recombination, where two atoms collide to form a weakly bound molecule, and the third atom simultaneously carries away the binding energy. By analogy, the dominant loss mechanism for polar molecules are exothermic two-body chemical reactions. The probability of such a reaction occurring can be described by scattering theory, and it depends on a quality called the impact parameter. In classical systems, the impact parameter is defined as the distance of closest approach in the absence of an interaction between the two species. As the two particles move in straight lines towards each other, the imaginary line connecting them rotates about their center of mass. As a result, the system has a certain orbital angular momentum, given by the separation between the particles and the relative linear momentum. We can relate the distance between the particles to the impact parameter, and the linear momentum to the reduced mass and relative velocity. Once in the quantum regime, the angular momentum of the molecules becomes restricted to integer values, which means that the available impact parameters are then also limited to quantized values. For zero angular momentum, Head-on collisions with zero impact parameter are possible, thus facilitating the chemistry. If the molecules have any non-zero angular momentum, on the other hand, they are kept apart by a centrifugal potential. Even for cold molecules, one can only observe scattering outcomes averaged over a continuum of impact parameters from many angular momentum components, or so-called partial waves. Ultimately, one would like to see the scattering from each of the partial waves separately, and this can be achieved by the means of ultracold chemistry. The allowed values of angular momentum in a collision event depend on the nuclear spin states of the molecules involved. The nuclei are comprised of protons and neutrons, which are both spin-half particles. The isotopes with an odd mass number have a half-integer nuclear spin quantum number, which makes them behave as composite fermions. This means that they have to obey the Pauli exclusion principle, which states that two identical fermions cannot occupy the same quantum state and therefore are forbidden to come into close contact. The minimum angular momentum value they can have is therefore 1. The isotopes with an even mass number behave like composite bosons and are free to collide because their minimum allowed angular momentum value is 0. Ultracold chemistry has so far been mostly limited to alkali metals. For example, potassium-40 is a boson, while rubidium-87 is a fermion, so that the molecule made of these two atoms has fermionic properties overall. The experiment involved 2 scattering events between 2 potassium-rubidium molecules. If all the colliding molecules were in identical quantum states, the isotropic centrifugal potential barrier was seen to slow the rate of the reaction down. If the particles were prepared in 2 different nuclear spin states, on the other hand, the restriction to the L=1 angular momentum scattering was lifted, which resulted in a change to the shape of the potential energy surface. The energy barrier was increased for side-on collisions, but decreased for head-to-tail collisions, which made the reaction proceed much faster. This is the first experimental realization of how the geometry and the dynamics of chemical reactions can be controlled down to the quantum level.
Usually, chemical reactions involve ensembles of atoms. We mix a lot of reactant atoms together and hope that under the right conditions, we will obtain our products. In May 2019, scientists at Harvard University were able to combine precisely 2 individual atoms into a single molecule. They used optical tweezers to isolate 2 individual atoms of sodium and cesium and bring them together to make exactly 1 molecule. They began with 2 isolated cold atoms in an optical tweezer, where the highly focused laser beams were used to keep the atoms immobilized. Then, the atoms were brought together into a single optical tweezer to make a so-called optical beaker. The reaction was carried out through photoassociation, a technique which we covered previously. The colliding sodium and cesium atoms were optically excited with a laser and absorbed a photoassociation photon. This enabled the molecular transition and the formation of the excited cesium-sodium molecule. The excited molecule quickly decays into the ground state, emitting another photon. By looking at the resulting fluorescent signal, the researchers could spectroscopically confirm whether the reaction occurred. By cooling the molecules down, we've seen that we can lock them into single quantum states and have complete control over the molecular degrees of freedom.
Yeah, and we also saw that there are a variety of ways of producing them. We've looked at direct methods such as buffer gas cooling and stark deceleration, as well as looking at one indirect method, photoassociation.
And although the field of cold molecules is just starting to heat up, we've shown a number of pieces of research that explore what we can do with them. Right, Simone?
That's right, Paulina. The scattering experiment with potassium-rubidium fermionic molecules demonstrated that the reaction rate can be controlled by manipulating the nuclear spin of the collision partner. Also, molecular tweezers have been applied to cold atoms to make, for the first time ever, a single molecule in an optical beaker. I mean, that's pretty neat.
So now that we know what happens to molecules as they're cooled down and combined, we have the tools to control them at the quantum level. This means that we can perform detailed spectroscopic measurements and gain a higher understanding of select molecules.
Sure, and we can look at things like reaction barriers, transition states, and other interesting properties. We can also use cooling to control the chemistry, giving us the opportunity to construct new quantum materials.
The field of cold molecules is truly exciting, with endless possibilities in terms of fundamental research of chemical physics, as well as multiple applications in quantum computing, optics, and materials.
And that is why cold molecules are so cool.